Thank you, Wack. Thanks for the introduction. It's been a really nice morning so far, morning and afternoon. Despite my slides being extremely orange, this this project and this talk is probably the least rocket pool related of the ones on the agenda. But I thought, I mean, since I'm part of the community, I wanted to share what I'm doing, and I think there's some people here who might be interested in learning about it. Right, so I'm going to get right into it. So the title of the talk is the name of the project, which is Ethereum, and that means formal verification of the implementation correctness for applications that run on Ethereum or the Ethereum virtual machine. So it's kind of a portmanteau of the two words verification and Ethereum. So I wanted to just go through like this. This is quite a mouthful, or there's like many concepts in this description of what I'm doing. So I wanted to go through and say what I mean by each of those. As Wax said, I don't have that much material to talk about. I'm more interested in getting questions and like going through it in a more Q&A style. So when we get, I've got like 5 slides. When we get through the slides, we can just go straight into Q&A. Okay, but let's start with formal verification. So formal verification means mathematical theorems where the theorems are checked by a machine. So we have a piece of software called a theorem prover, which does the checking, and it's doing the checking right down to the lowest like axioms of logic. And we can do that. We can automate that using computers, so that's why it's a feasible thing to do at all. Although it's still like quite a big deal and quite slow. But it gives you an extremely high assurance that the thing that you've proved is actually true. And yeah, it's way more than you get from any other process. So what we're doing formal verification. What are we doing formal verification of here? Formal verification of the implementation of Ethereum applications. So what I mean by the implementation is the bytecode, like the actual code that ends up on chain as the code for a smart contract. And so that'll be like the code for all of the smart contracts that make up a protocol or a DApp. So in the case of Rocket Pool, it's like a huge suite of like more than 30 smart contracts. And all of those are compiled and deployed on chain. And then there's the bytecode sitting on chain. And that's the actual implementation. Like that's the thing that the Ethereum clients are running whenever you do a transaction that interacts with these smart contracts. So we're going to go straight to that source and say, like, this is the source of truth of what's actually running. So that's the thing we're going to verify. Okay, next terminology here is correctness. What do I mean by correctness? So here I mean we're going to prove a theorem that is a true fact about any execution of this code. Whether that's correct from the perspective of the user or like the perspective of what the protocol wanted, there might be a little bit of a gap there because that's more of a subjective thing. But the thing we can do is objectively prove mathematical properties about execution. So in particular, that it conforms to any desirable properties that we have the patience and expertise to specify precisely in logic. And of course, I would be very happy to work with any protocol and like try to figure out like what should your specification of correctness mean? What kinds of properties might be useful to prove about this project? All right, application. What I mean by application, I think I've talked about this a bit already. It's like a DApp or a protocol or like any suite of smart contracts that are implementing something. This could range from very small, simple single contracts like the wrapped Ether contract, for example. It's just a token contract. It's very simple to understand. Or Rocket Split, which is a project that I've worked on. This is a contract that's designed to be a withdrawal address for a Rocket Pool mini pool. And yeah, it's just like a single contract. It's supposed to do one job. But it could range all the way up to a much larger protocol like Rocket Pool itself, like all of the Rocket Pool smart contracts, or another big protocol like, Uniswap, or what's another good like on-chain example? I mean, there's a ton of on-chain things where they use lots of smart contracts. Sometimes they'll use off-chain things as well, and then it starts getting a bit harder to integrate. But basically, what you would have to do is take what we've got here, Ethereum, and also model out enough of the stuff that's happening off-chain in order to have a complete verification story for that protocol. In the case of Rocket Pool, we already have a little bit of that in that Rocket Pool depends a lot on the state of the beacon chain. It's not just EVM. But since the EVM is like starting to get the beacon state root and stuff in that, we'll have to model some of the beacon chain anyway. And yes, the last thing is the EVM. So the EVM is currently, that's the virtual machine. It's a very nice virtual machine. That is the execution environment for applications that run on Ethereum. It's also used on other chains. So many Ethereum layer 2s will also be using the EVM or some version of the EVM. So hopefully this work could be extended to verify protocols on other chains as well. But initially, I'm going to focus specifically on just Ethereum L1, EVM. And it's a nice place to be because that is not it's not like a machine that like a typical desktop like x86 Intel CPU or something, which is a lot more complicated to reason about. The EVM is very small, very simple instruction set. So it's kind of a sweet spot because there's a lot of value in the protocols that people are using. Like there's a lot of TVL, there's a lot of money at stake if you have a bug in your protocol, but also the thing that you have to verify is very well specified. It's very small. Yeah, so that's nice. Ken, how do I move the thing? Oh, there we go. All right, so now let's go. This is a big slide, but it's just an example, and it's not even a real conjecture. It's just to give you a flavor of what I'm talking about when I say I'm doing verification of things, and I'll be going through this in a lot of detail. So don't feel like you need to follow what's going on initially. But so yeah, the abstract goal of the project is to be able to prove any functional property of EVM bytecode in a partially specified context. So what I mean by that is a functional property is just like something that's well specified enough that I can write it down in mathematics or in logic. EVM bytecode, we talked about that before. So like we're going to be proving properties of the execution of EVM bytecode, meaning we're proving properties of what happens when a transaction happens on Ethereum. And this partially specified context thing, what I mean by that is we want a theorem that kind of we can prove once and for all, and then it applies in many different contexts. Like we want to say this holds kind of whenever these assumptions hold, and you can vary all kinds of other stuff. Like other people can be doing other transactions. The state of the whole like the whole Ethereum state might have changed in all these different ways, but as long as we never made any assumptions about that state, this theorem still holds. So you kind of get a lasting fact about whatever you're trying to prove. So for example, if we wanted to do for rocket pool mini pools, a nice property we might want to prove about those is that the balance of the mini pool can never be drained somewhere else. Like you can't have an attacker come up with some clever transaction and say, well, I figured out a way to kind of coax the mini pool into sending all of its ether to me. So that's an example of a nice property we might want to be true of a rocket pool's mini pools. So I haven't proved this. Like I'm not at that stage yet. I just wrote down what I thought it might look like. So there might be typos in this. And like when it's done with a real theorem prover, of course it'll be solid. But like just to go through this example, we can look at the thing at the last 3 lines. That's the conclusion of the theorem. And then the stuff above the arrow is the assumptions of the theorem. So you kind of explicitly list all the assumptions you're making about the state of the machine. And then you state like, what do you want to be true? So let's focus on the conclusion first. The conclusion here, I'm saying that if we take the mini pool, which is going to be a smart contract, and look at its balance in the state of the machine. So I'm calling the state of the machine this variable m. That's the machine state, and every contract, every address in Ethereum has a balance at all times. And so we've kind of got 2 machine states here. We've got the m, which is the state before the transaction happens, and we've got the m prime, or the m with a little dash next to it. That's the state of the machine after the transaction executes. So the first line here is talking about the change in balance of the mini pool. So it's saying if the balance of the mini pool before subtracted from the balance of the mini pool after. So what would happen if the mini pool's balance, like ETH balance, goes down. So somehow ether came out of the mini pool. We want that always to be less than or equal to the amount of ether that went into either the Rocket ETH contract, like the token contract that's going to Rocket ETH holders, or to the withdrawal address of the node operator who's associated with that mini pool. So this is the conclusion of this theorem, is kind of saying whenever the mini pool balance goes down, it must be compensated by at least an increase in the balance of either rETH or the withdrawal address. And that kind of implies that the ether can't have gone anywhere else. Like you can't leak funds out of the mini pool. So ideally, I would want to be able to prove some property like that. We could get into more fine-grained properties and say, like, actually, here's what the split should be. Like this much should go to rETH, this much should go to the withdrawal address. But even a property like a generic property like this is nice to have because you know, like, okay, there's no way I can craft a transaction that would break this. And then what's above the arrow, that's all the assumptions that I think that you would have to make in order to prove something like this. So we're not going to make assumptions about the entire state of the chain because that would both be a lot to deal with and also not very applicable because the state of the chain is changing every 12 seconds. It's a new state. So we make kind of the minimum assumptions that we would need to make in order for this property to hold. So what I was thinking, I haven't proved this yet, but what I was thinking it would probably come down to is that we've got the actual bytecode of the Rocket storage contract and the minipool base and the minipool delegate are all there in the machine at the addresses that we expect. And if you were to look up the node address and then look up its withdrawal address, that comes out with the current withdrawal address for that minipool. So that's where we get the withdrawal address from. And then the last bit is, oh yeah, and we also look up like the Rocket token rETH address to get the current rETH address. I mean, that one never changes, but we just want to say we're making an assumption that the rETH contract is implemented at that place. And then the last line of the assumptions is this execute TX, which will be a relation. Like that's the thing that I need to define in logic to say, what does it mean to execute a transaction? And I'm saying, if you execute this transaction TX, it actually finishes, it doesn't revert, it comes out with the results, and the new state of the machine is M prime. And I didn't make any other assumptions about TX. TX is this variable that represents the transaction. So up the top, I've got all of my universally quantified variables, and I don't make any assumptions about them apart from the ones that are listed. And since nothing is listed for TX except for the fact that it executes, this kind of encompasses all transactions that anyone could do. So it could be from any sender, it could be with any data, it could be with any value, doesn't matter. So that's how you can get a theorem like this to cover like a lot of possible scenarios and still give you the property that you want. Right, so the rest of the slides are like a lot less detailed. It's just an overview of where we're up to. So the plan is to be able to prove theorems like that. The plan is to build a formal model of the EVM in logic, and I'm using higher order logic to do this. In particular, using the theorem prover, the higher order logic theorem prover, sometimes called Hall 4. It's a nice environment for building mathematical theorems like this. It's got a lot of background libraries, like it's got libraries for mathematics, just generic mathematics. So lets you define data types and bytes and bits. And there's a little bit of like cryptography stuff that is not in the libraries that I'm working on right now that I have to add. But a lot of the stuff that I would need is in there for reasoning about programs in particular. But yeah, so that's like the bulk of the work is build a formal model of the EVM. The second step after that, after we've got like a pretty good EVM, I would say, is to add a layer of what's called separation logic, which is just like a conventional way of organizing your reasoning when you're dealing with partially specified contexts. So you want to kind of prove something and say, here are the assumptions I'm making about it, and the rest of the world can be anything at all. Separation logic is a way of organizing that style of reasoning. And I have some prior work that's been used for program verification for machine code, like not EVM code, but like machine code that runs on CPUs, that I'm using as inspiration for how to do this thing. And the last step, which I think is pretty interesting, is what's called decompilation into logic. So this is a way, so previously I said like we're just going to verify the bytecode, which is the actual implementation that lives on chain. But most developers don't ever care about bytecode. Like we don't want to look at it as too low level. We don't want to reason about it. That's looking like the individual opcodes of a contract. Most people want to be thinking at least in terms of a high level language like Solidity or Viper. There's the Huff language, which is like kind of in between. It's a bit closer to the bytecode. And then there's just like the actual bytecode. It's way down at the low level. This decompilation into logic idea is a way of bridging the gap between the really low level bytecode and something higher level like Solidity, or even higher level than Solidity, something just like looking at pure maths. Decompilation into logic is a way of taking some bytecode and automatically inferring some functions that are equivalent, like some high-level functions, or like Solidity code, you could say, which are equivalently, which have the same semantics as the bytecode that you started with. So you can kind of take the bytecode that came out of the compiler. This means like we don't have to trust the Solidity compiler at all. We don't have to trust any compilers. We start with the actual source of truth, the bytecode. We run our decompilation into logic thing, and that produces a theorem that says this function, this high-level function, has the same semantics as that bytecode. And then you can reason about that high-level function, and all of your reasoning will transfer down to the bytecode because it's backed by the theorem. So that's one piece of automation that I think would be very helpful for doing this a bit more scalably. All right, so where are we now? I've been working on this on the side, I would say, for the last few months. I haven't really touched it in the last half a month, but I was working on it more intensely around December. I have defined the Ethereum virtual machine in higher order logic for the most part. Like I wrote down what I think it should look like. I put all the opcodes in. I may be missing like 3 or 4 opcodes. And I'm missing most of the precompiles, which are these, they're also part of the EVM, but like they're not opcodes themselves. They're just like contracts that are assumed to exist, like for example, for running SHA-3 or doing like an elliptic curve signature verification or something like that. So I've defined most of that in higher order logic already. It's on GitHub. It's there for people to look at if they want to. I haven't tested whether it actually is correct. Like this is the kind of the core of the project. We need to know that our model of the EVM is the same one that the Ethereum clients actually implement. Otherwise, we're proving against something that's not real. So the next thing that I want to do is take the test suites that the clients actually use to test that the clients are correct, and try to run them all against my model in logic, just to give some assurance that we're modeling the same thing. Like we've got an EVM that's the actual EVM. And yeah, so that would be the next thing, is to figure out how to get the Ethereum client tests and run them on the logical model, and then add the extra pieces as necessary. Like we'll have to do the precompiles. We might have to do a few more opcodes, maybe a few other features. By the time Dencun comes in, we'll have to do like whatever's needed for the blobs, whatever's needed for the beacon root when that comes online. And then it's just following the plan, like figure out the separation logic, figure out the decompilation, and try it out on a few contracts. Like probably start small, do the wrapped ether contract, for example. I want to personally build like a smart contract wallet to use for myself, so I don't have to use, everyone uses like Gnosis safes. I think they're good, but they're also like overly complex for my taste. I'd like to build my own wallet and store for my cold storage, but I wouldn't want to put any significant funds in there without formally verifying it. So that's one thing I'm planning on doing. And then kind of the future directions for the project is, what can you do if we have something like this? And I think there are 2 big obvious directions for what to do with it. One is to go after bug bounties. So there are millions and millions of dollars available, for example, on Immunify for people to try to break projects, find bugs in them, if you find any critical bugs. So there's no guarantee that there are any critical bugs, but if there are, one way to find them kind of systematically is to go to the project, try to verify it, try to check that all the properties that you think should hold of this protocol do hold. And in the process of trying to prove those theorems, if they're not true, you will find out why they're not true. The process of doing the theorem proving kind of tells you where the problem is. So that could be like a way of systematically claiming bug bounties where possible. And the other thing that we could offer is an alternative or a complement to auditing services. So if you have a new implementation that you want to know is correct, you can pay auditors to look at it very closely. You could also pay someone using Veriferium to not just look at it closely, but like prove some theorems about it. And then you'd get very strong assurance that what you're doing is not going to have any bugs. All right, so this is my last slide, is that this is kind of just me at the moment. I have some friends in the whole 4 theorem proving community who are also like contributing little bits, but it's mostly me driving it. I would love people to come join. Collaborators very welcome. The whole model is going to be completely free software. And since this is like a combination of 2 very deep technical topics, one of them being formal verification in higher order logic, and the other one being the Ethereum virtual machine and like low-level smart contract execution, I don't expect anyone to know how to do these things. No experience is required. Just a lot of enthusiasm and willingness to learn and contribute would be very welcome for people to join on this project. The code is currently hosted at my GitHub here. Thanks.
Thank you so much, Ramana. We've got a question here that we're going to get started with. And then if anyone else has any questions, please put your hand up so I can see you.
Yeah, this looks great. Thanks for sharing. As someone who's not familiar with formal verification of contracts, but familiar with solidity testing techniques, things like fuzzing, invariant testing, is this like basically just a more complete way to verify functionality, invariance?
Yeah, you can definitely think of it that way. So this is more complete, more thorough, a lot more labor intensive actually too for that reason. But it's kind of like, yeah, it's once you get a theorem out, then it's kind of covers everything. Like it's exhaustive. You haven't missed anything, and it holds forever. Of course, if you upgrade your code, then it's no longer valid. But you can try to prove the same theorem for the upgraded code. So like compared to fuzzing, we are instead doing like universal quantification. Like we're covering all of the possible. It's kind of maybe closer to symbolic model checking or something like that. Like you're covering all of the possibilities at once by using a universally quantified variable. But compared to testing, it's similar in a way in that in the tests you kind of specify what you want to be true, and then you try it for like a few values. Whereas here you would specify what you want to be true, and then you would prove it for all values.
There's another question right here, so just one moment.
Yeah, for non-technical users, once it's deployed, is there anything about Verifium itself that requires trust?
Yeah, good question. So Verifium itself will be written primarily. It will be written as theories for the Hall 4 theorem prover, and those can be independently checked and looked at. So the main thing that you're trusting is the theorem prover and the logic that it sits behind. And this theorem prover has a particularly strong trust story for like why you should trust it, which is, well, there's kind of two components to it. One is that it can emit independently checkable proofs, which you can write your own theorem prover or use another theorem prover to check the proofs. And the other one is just the way that it's designed. So it's designed in what's called the like LCF family of theorem provers. I forget what that stands for, but basically how it works is that it uses strong type checking to ensure that every theorem value that gets computed by the theorem prover has the type theorem, and that type can only be produced by a very small number of functions in what's called the kernel of the theorem prover. And each of those functions is an inference rule in logic. It's like one of the low-level inference rules of logic. So no matter what you do in your theorem proving activity as a human user at the top, if you get one of these theorem values out, you know that somehow it's gone through that kernel and every single step has been checked as being a valid inference rule. So yeah, I've done work in the past also on verifying the theorem prover. So you kind of get like who trusts the verifiers kind of questions. But yeah, this is, I would say, way higher in terms of assurance than you would get from most other projects.
We've just got one last question and then we're going to move on.
I'm wondering if you're aware of any smart contract auditing teams that are already using like an approach like this to verify, smart contracts, and if not, why not? Is there a gap in the industry that this type of approach could fill?
Yeah, that's a good question as well. So I haven't looked too hard into it, but I am aware of some companies or some groups that are doing, like, formal verification is well liked in the crypto community more than it is in other areas of industry, which I think is a good sign. But yeah, there's a company called Runtime Verification, which does something like auditing and theorem proving, and they use the K theorem prover framework. And I think, yeah, there's also, like, I know there are people who have, for example, verified wrapped ether, but using their own framework. So two things I would say about it. So one is that I think the approaches that people tend to use are not as high trust as the not as trustworthy as the one that I'm intending to do. So they kind of use a less trustworthy Ethereum prover, or they use something that like requires more assumptions. And the trade-off that they're going for there is that they want it to be more automatic and faster and easier to get the thing done. Whereas my way is like very expensive in terms of like amount of labor that you would need to put in to get it to work. I would be interested in automating as well, but I kind of want to do it right from the start. And that kind of answers your second question as well. It's just like, why is there this gap? Like, why aren't people doing this already? I think it's just the cost. And so their Ethereum could be kind of a public good in the sense that once you build the model, that's like a lot of shared cost across verification projects in the future. So if we all come together to like build this model and kind of maintain it and keep it up to date with the Ethereum execution specs, that would alleviate some of the cost of doing this in the future.
Thank you so much, Ramana. That was wonderful. Guys, can we all give Ramana a round of applause, please?